So this is a gravitational field theory question, right? So the first one is for A, outline why the gravitational potential is negative. And the basic idea is what I guess when two masses are infinitely far away, right? When they're infinitely far away, their potential is zero. Okay, and if they get closer to each other than infinitely far away, it requires work to get them to infinity, right? So if you've got to do work to get it to infinity, doesn't that mean that if they're somewhat close to each other, that's a negative potential? You know what I'm saying? Anyway, that's sort of the argument that you need to make. And I did make 2 points there, right? That infinitely far away would be zero potential, right? And then if they got closer, you'd have to do work to get them apart, right? Whereas remember, two charges, if these were two positive charges, um, uh, we'd have to do work to get them closer together than infinity, right? We wouldn't have to do work to get them back out to infinity. They'd do that by themselves, right? Okay, and then let's see, show that this is constant. Well, okay, we can do this. So if you look at on page 10 of your data packet in subtopic 10.2, this is actually the first equation there, right? You get that the gravitational potential is minus gm over r, right? Okay, so this is instead of vg, we're just going to say vs, right? The potential of the sun, right? Well, if I multiply both sides by r, what do I get? Think about that, right? Multiply both sides by r, don't I get rg equals minus gm? Well, this is a constant on the side, right? So just show that manipulation, right? Now that you have this, right, this says calculate the gravitational potential of the Earth in its orbit around the sun. Give your answer to an appropriate number of sig figs, right? So what you're going to do is you're going to use this, and they often do this. They'll set up some relationship. They'll say, show this relationship, and then now we use that relationship, right? So I'm going to go radius at the sun, right? Potential at the sun's surface equals the radius at Earth's orbit, right, times the potential. These are not velocities. These are the gravitational potential of the Earth at its position around the sun. So here's the sun, right? Here's the Earth orbiting the sun. Here's the Earth, right? So step one, use that, and you'll get that the potential is something like 8.86 times 10 to the 8th joules per kilogram, right? And I thought that I didn't read this question, so I got it wrong. So I thought it was find the gravitational potential, but it says find the gravitational potential energy, right? So remember that the potential energy is the mass times the potential, right? So the gravitational potential is the mass times that, right? So the next step is once you find the potential at the Earth's surface, right? You are going to, and notice that they give you the potential at the sun's surface, right? So that's what you're going to put in. Sorry, this is a little bit disjointed, right? That's what you'll put in here, right? And then 7 times 10 to the 8th is what you'll put in here. Right, the Earth's distance is this. Put that in there, and then you can find that, right? Okay. And then you're going to take that answer for VE, right, and put it in here. And then put the mass of the Earth in here. There you go, right? And then that'll give you the potential energy. That'll be a big negative number. Okay. Well, that's interesting. I didn't write down a negative number. Should be negative, right? Okay, I haven't looked at the mark scheme. I don't know whether they ding you for that, but there it is, right? Okay, so there you go. And then it says appropriate number of sig figs. Well, look how many sig figs there are there. Make your answer have the same number of sig figs. Apparently, they only enforce that like when they say they're going to enforce it. So.